Welcome to the numerical analysis course. We are studying different methods, different iterative methods under numerical analysis. In our previous lectures, we have been studying bisection method. We have studied bisection method, regular falsy method, and Newton-Rafson's method, which is a special case of fixed point iteration method that we are going to study today. Fixed point iteration method is a very simple iterative method where we are given an f of x, the function f of x, and like we have been doing in the previous methods, we have to find its root, the point where f of x is equal to 0. Right. For that, we'll put f of x is equal to 0 and we'll rearrange terms. We'll put f of x is equal to 0 and then first we are going to put f of x is equal to 0 and then we'll rearrange terms such that x is equal to some other function g of x. Given this f of x, we'll put it equal to 0 and we'll rearrange terms such that we have x on the left hand side and something else, everything else on the right hand side, and we'll call that g of x. And then we'll iterate by putting x sub n plus 1 is equal to g of x of n. This means that x at the next iteration, at n plus 1th iteration, would be the g computed on nth iteration, and we'll repeat it until convergence. So this seems a bit mathematically difficult or difficult to understand, or a bit mathematically complex steps. So let's try to understand these steps further with the help of example. Right. We have an example in this lecture. We'll solve two examples. The first example is where we are given this f of x, and we'll apply this step number 1, f of x, put f of x is equal to 0. So in step number 1, I'm going to put f of x is equal to 0. X squared minus x minus 1 is equal to 0. Right. Starting with this, we can write x squared. We can take this x minus 1 on the right hand side of the equation. This becomes like this, and we can divide this whole equation by x. So this leaves us x equals 1 plus 1 over x, which is our g of x. So x is now g of x. So now we'll iterate this for x n plus 1 equals g x of n. So for iteration number 1, and we can write like this, x n plus 1 is g x n, means 1 plus 1 over x n. So at nth iteration, if you are given, for example, a given value of x, we'll put that here, and in the nth iteration, and x at n plus 1th iteration would be computed by this expression 1 plus 1 over x n. So let's execute it. Let's execute it with the help of these steps. So step number 1, let's execute step number 1. Let's execute iteration number 1. Since we know that all numerical methods are iteration based. So in iteration number 1, we'll put x 1, maybe we are given x1 is equal to, I have executed it for you, and if x1 is equal to, let me check, fixed point iteration method. So this is how I have implemented it. I have started with x is equal to minus 5. So x1 is minus 5. At iteration number 1, at the end of iteration number 1, or x1 is equal to minus 5, we can write it here, and then we can compute, in this step, we'll compute xn plus 1, x2, that is equal to 1 plus 1 over xn. That is 1 plus 1 over minus 5. So this is 1 minus 1 over 5, 5 minus 1 over 5. That is 4 over 5.8. So this is x2. X2 is 0.8. So in iteration number 2, we'll start from x2 and we'll find x3. So x2 is given to be 0.8 and we'll find x3 is 1 plus 1 over xn, 1 plus 1 over 0.8. So this gives us 2.25. And we can keep on going like this, and I have written a Python code for this and I have made it available for you last night, and you can run that code for multiple iterations. My code runs for 10 iterations. The code that I have provided you runs for 10 iterations, and at iteration number 7 it becomes 1.62. So the output is like this: iteration number 1, xn plus 1. So when we start, this is -5 and this is 0.8, and iteration number 2 we start with 2.8 and 2.25, and at iteration number 7 this becomes 1.62, and at iteration number 1 this is 1.61, and at iteration number 9 it's also 1.61. So let's see whether it has converged. It seems it has converged, but to verify that it has actually converged, we need to plot this f of x to graphically see the roots. My Python code also plots, my provided Python code also plots this f of x versus x. Okay, and it is plotted like this, that it has one root at -6, it plots like this. One root is at -0.63, the other is at positive 1.61. Here we have 0, x equal to 0. So this function has two roots. This f of x has two roots. One of the roots is at plus 1.61, the other is at -0.63. So this xn plus 1 is equal to gxn, g of xn. It has converged, starting with xn is equal to -5. You can have a different starting point, or you can choose if you are running my Python code, you can start with a randomly selected. If you are using my Python code, you can start with any randomly chosen starting point. So this is not always the case, or it's not mandatory to start it from -5. You can start it from anywhere, and if you are using this xn plus x7 plus 1, she'll be converging to 1.61. So you can try different starting points in my Python code and you'll reach to the same answer, 1.61. That's interesting, right? So but it is not the only way we can find x sub n plus 1. If we start working with this polynomial, f of x is equal to x squared minus x minus 1 is equal to 0. Previously we shifted this minus x and minus 1 on the right hand side. Alternately, we can do like this. We can take this x common, x minus 1, and we can take this 1 on the other side of the equation, becomes 1. So x can also be written as 1 over x minus 1. So which is of course g of x. So starting from the same f of x, putting it equal to 0, now we have reached to a different point, and we'll write it like this: xn plus 1 would be g of x of n, or xn plus 1 is 1 over xn minus 1. So let's see whether if we use this x sub n plus 1, this expression for x sub n plus 1, instead of using this expression, let's see whether we reach to the other root. We know we have two roots for this f of x. One of the root is at minus 0.63, the other root is at 1.61, positive 1.61. So this, using this, we have reached to the second root 1.61. Let's see whether we reach to this negative root if we start working with this. Let's see. So maybe we work with the same. We start with the same starting point, but you can start from any starting point. You can choose your own starting point. Let's make things simple and start with the same starting point, minus 5 that we started with for the last expression for x sub n plus 1. So iteration number xn minus 5, and if we put it minus 5, let's see what is iteration number 1. Start with iteration number 1. So x2 would be 1 over xn minus 5 minus 1. So this is 1 over minus 6. So 0.166 minus 0.16. So this is minus 0.16. And then we'll start from minus 0.16 and put it here. So in iteration number 2, we'll start with minus 0.16 minus 1 minus 2.16 and so minus 0.85 minus 0.85. So my Python code runs for 10 iterations, and finally in the last 3 iterations, 8, 9 and 10, 8, 9 and 10, this comes out to be minus 0.61, seems to be converging at this point. And this point is a very special point because minus 0.61, minus 0.63, it's not minus 0.63, it's minus 0.61. So it seems to be converging at this root. So this expression, this alternate expression for x sub n plus 1, it now converges to the second root, minus 0.61, or you can call this as first root or this as second root. It's your choice, but the other root. So this expression, when worked with using iteration, it converges to this root, and this expression, when worked with iteratively, it converges to this root. So now we have reached to both roots, right? But we can work with the same. F of x using one other way. So given this f of x is equal to this, let's put x squared is equal to x minus 1, or x is right, keeping x here and taking this plus 1 on the other side of the equation, this becomes x squared plus 1, which is equal to g of x. So we can write it as x sub n plus 1 is equal to g sub xn or xn squared plus 1. So this is another way we can compute x sub n plus 1. So if we go on with this x sub n plus 1, and we start with the same starting point minus 5, if we reach to, it becomes 24 575, it becomes 24 575 something, and it goes on and on. It doesn't converge. The values become very large because we have xn squared. So xn squared is, as x increases, xn increases, this value increases, because square is a very large value. Square of a large number is really a large number. So xn squared plus 1 is a large number. So if you go on, the numbers become very large, and this x sub n plus 1, it never converges. It doesn't converge. So we have worked with, given this f of x, we have applied these two steps, and we have worked with these three expressions for x sub n plus 1, and one of them, expression number 1, it converges to the root 1.61. The second expression, it converges to minus 0.61, the second root, the other root, but this doesn't converge to anywhere. Right, that's all for this lecture, and in the next lecture we'll work with another interesting example using fixed point iteration method. Thank you.